Hello and welcome to my server room monitoring system final project bench assessment. My name is Simba Nyakambango and I'll go through the project and which aspects that I personally helped in the project for the final lab report submission. There are three main aspects of the project: access control, power control, and thermal control. The last two, power control and thermal control, were constant checks that were occurring in the main, making sure that these two aspects were always kept in check and always kept as they needed to be. And if any difference or any anomality was faced, these would be signaled by different LEDs. Access control was the setup phase, which included an admin entering passwords into the system, and then the gaining access part was asking a typical user to enter their password for them to be able to access the room for 1 minute or inhibit the access of the room. Power control was simple measuring of constant input from a potentiometer and gaining those readings. Thermal control was a measurement of temperature from the surroundings and getting the average of those temperatures and outputting them as well and signaling if need be. This is an overview. As you can see, our hardware implementation as well as our simulation, which the signaling LEDs here were a yellow, green, and red LED, which was used in this project. As we used the virtual terminal as our serial communication and simulation, whilst as in hardware implementation, we used a Bluetooth terminal and we used a Bluetooth chip. We had three distinct UML diagrams. The main program UML, which showed the overview of the whole project. This showed us this shows how the project runs typically in the main. So it checks the voltage and the temperature constantly, and this does not change no matter what else happens in the system. Whilst E2P-ROM gaining access or admin setting up passwords occurs at the very beginning or at the very end. This is the main program UML activity diagram, which can be seen in our lab report. We also had two other UML activity diagrams, namely the timer 0 operation and the timer 1 operation of the UML activity diagrams. Timer 0 worked as a 1 minute interrupt, 1 minute interrupt for the system to either gain access to a door or inhibit the access to a door. This was signaled by a green LED. Timer 1 worked as a 5-second interrupt, which worked as a measurement aspect. So every 5 seconds a measurement would be taken, and this was for the temperature calculations that needed to be done before the 7th segment and the averages were calculated. And these two flowcharts as well can be seen in our final lab report, which shows the different flags and different registers that were used for timer 0 and timer 1 and the sequence of events. The software development was where, as I talked about, the timer 0 was a 1 minute for access control and timer 1 was a 5-second for thermal control. We used this constantly, and these were a vital part of our project. We were able to use these using the defined interrupts and the defined flags to make sure these were operating properly. Another important part of the project was E2P-ROM, working with E2P-ROM, which is memory space where even if the system is shut down, these memory addresses will always be kept there and always be kept safe, and always make sure that these can be used by anyone. The relevant calculations were done with accuracy, and these can be seen in the later slides and in our final report. I personally did the calculations for the voltage control, as well as helped out in the use of E2P-ROM and the rest of the code as well as a support system. Timer 0 can be seen here. Timer 0 used a timer frequency of 5 megahertz, and then because the prescaler value was 256, we were able to take to divide and get this value here, and we would loop through this value and decrement till it gets to 0, which would give us 1 second. For 60 seconds we simply had to loop 60 times, measuring the overflows. As mentioned in the slide before, we were measuring the overflows in terms of loops. So here, because timer 1 has a prescaler of 8, we could only use the maximum of 8 as a prescaler. So we got this value, and we would loop through the system 50 times for us to be able to get 5 seconds. This is the way that we did it, using these interrupts and these flags as well, clearing them and then setting them after we've done each operation every 5 seconds. This is the Proteus simulation. As you can see, a virtual terminal here. We did an average temperature which measured every 5 seconds there was a reading of temperature, and after 25 seconds we would get the average of those saved temperatures, and this can be seen in our code, and it's working perfectly. And you could see on the 7th segment the temperature that has been measured. The LED was being turned on only when the voltage was 2.5 volts, below 2.5 volts, and the way we're changing this voltage was through a potentiometer. And as soon as the potentiometer was below 2.5 volts exactly, we were able to get it to 2.499, which was the calculation that I did as well. When we got to 2.499, we were able to turn on the LED immediately. This shows how we allow the user to enter the password, as an admin would enter and save the passwords, and then ask how many people want to enter the room, and then according to the choice made by the admin, then would allow the user to enter after putting the correct password, of course, turning on a green LED for 1 minute. This was also the same. As you can see, this is a Proteus simulation. This is E2PROM, which shows the memory addresses saved. So each digit is saved in its own address, and this was easy because we took them from an array. So we saved them into an array and then put them into E2PROM from that array. So each and every digit is in its own memory address, and this can be seen here. And you can see the equivalent ASCII values here, which is 1, 2, 3, 4, 5, 6, 7, 8, and 2014. And these are the values of the E2PROM that we used. This can be seen in our video for the simulation, as well as hardware implementation. Hardware implementation is, just as I explained, the same as, or it's exactly the same as simulation, just in the hardware implementation. The only difference was, instead of a virtual terminal, we're using a Bluetooth for serial communication. As you can see here, we have got our potentiometer here, which was for voltage, and we've got our LM35, which can be seen here next to the Bluetooth terminal for measuring. These are our 3 LEDs: yellow, orange, and green. This is the Bluetooth terminal that we used, which was showing here the temperature was above 20 degrees Celsius, so it was turning on a yellow LED as specified in the project specification and requirements. And lastly, we had a PCB. PCB was the gateway between the hardware implementation and a product which is viable for market. So I did some research, and I was able to create the PCB, as you can see here. This is my personal input into the project as well. The Proteus simulation environment was where we created the PCB. You can see the potentiometer and the resistors and LEDs here, as well as the crystal. The rest of the components we could not add directly onto the PCB because they were components. So what we decided was to put sills, which would enable us to just plug in these devices here. And the video of this can be seen in our lab report. These are the schematics that were used. So we created a bill of materials, which can be seen in our lab report, which showed the maximum amount of money that we would have needed to make this a viable product, including a few things that are added in there so that we'll be able to make it a viable product which can work in any situation. And the viability and uses in real life. So I researched on places where this could be very useful, which are server rooms, hospital rooms, and every different places. And I put these in the lab report as well. Health and safety concerns. There were two main concerns, which were the buzzer, because it makes so much noise, it has to be regulated by the European standards. And then we had the fire, because we're working with electricity, we had to be very careful on our fire aspects and make sure that things don't catch on fire with our system. These are our issues faced. The Bluetooth terminal only showed 2 lines, so sometimes it was a little bit of a big problem because some of the commands will not be seen by the user. The last 2 pins of port B were power pins, so when loading our code into, we needed to remove these pins for us to be able to successfully load it. We were not aware of this at the very beginning, so it was a little bit frustrating. Then the rest were about timer one, because we didn't have enough information about it at the very beginning, but then we're able to understand as we got help and guidance from different people and different places of research. And thank you very much for listening, and hope to see you soon. Thank you.